talk of the morning is by Alex Kontorovich, who is from Rutgers University, and he will tell us about the unreasonable effectiveness of thin orbits.
Okay, so thank you very much to the organizers for the invitation and the opportunity to speak here. My first time in Brazil. Actually, my first paper is in the bulletin of the Brazil Math Society with Yaakov Sinai. He had just been elected to the foreign member or something of the Brazilian Academy. Anyway, so I'd like to proselytize a little bit about thin orbits. So I'll try to give you a wide sampling of topics, sort of unrelated problems that at their core, it turns out, have something to do with thin orbits. And of course, I have to tell you what thin orbits are. So let's begin. So here are 6 problems. One is a quite recent problem formulated by Kurt Mcmullen just a few years ago. He calls it the classical arithmetic chaos conjecture, not to be confused with QUE. I'll tell you what that is. Then there's a slightly older question of Einsiedler, Lindenstrauss, Michel Venkatesh. And then some much older questions having to do with numerical integration and pseudo-random numbers. Then there's a problem in modular representation theory, Lustig's conjecture, and another problem in sort of dynamics and continued fractions called Zaremba's conjecture. So the point is these are kind of from all over the place, and we'll just very, very briefly visit all of them. Now, they're already interconnected somewhat because Zaremba's conjecture is known to solve these 2 problems, pseudo-random numbers and numerical integration. That's why the conjecture was formulated. In fact, recently, with joint work with Peter McNamara and Jordy Williamson, we connected Zaremba's conjecture to, in fact, counterexamples to Lustig's conjecture, as I'll explain in a second. But otherwise, the problems, okay, maybe they're already connected somewhat, so there's really 3 different problems. But in fact, they're all one and the same. So I'll formulate a certain local global conjecture. This is based on joint work with Jean Bergin, which has all 3 or all 6 of these problems as consequences. So it's kind of a unifying theme. Now the conjecture, so the thin orbit's perspective is that these problems are one and the same. The conjecture is still wide open, so that doesn't help us. But actually even partial results, partial progress towards the conjecture, or thinking about these problems from this point of view has some merit. So Mcmullen's problem is really too hard. You need the full strength of this conjecture to say anything about arithmetic chaos. But already a few years ago, we gave a density solution, I'll explain what I mean by that, to Zaremba's conjecture. And more recently, we solved this ELMV problem by some weak version, the so-called beyond expansion program. I hope I'll get to that at the end. So that's kind of the overview. The philosophy of thinking about these problems in the local, global, and thin orbits point of view comes from studying this picture. But I'm not going to say anything about that picture since too many of you have heard me talk about this picture. So let's move on. Okay. Let me tell you a little bit about Lustig's conjecture. Let's get into some mathematics. So what's the conjecture? Go in. Well, we'll see. We'll see. Okay, so this is about modular representation. So if you take some nice, when people are, this is early 80s, late 70s, people I think are just getting the inkling that maybe we can classify all finite simple groups. And of course, you do this through studying irreducible representations. Now, the most classical thing is, okay, I give you some quintessential, PSLN over finite field. What are its representations? We usually mean complex representations. But what about modular representations? And in particular, what happens if the characteristic, so if you're looking into vector spaces over Fp, or Fp bar, where P is the same as the characteristic is the same as this characteristic, okay? So that was one of the types of questions that people were trying to answer. And Lustig gave a beautiful conjecture, which is this identity. In the interest of time, let me not say anything about either side of this identity. It's just some equality. Some characters can be recovered from affine Kazhdan-Lustig polynomials. So there's some identity. And the conjecture is that this identity holds as soon as the characteristic is large enough relative to the Coxeter number, okay, given an arbitrary group and finite field. And how large is large enough? Well, conjecturally, as soon as the characteristic exceeds the Coxeter number, or maybe as soon as it's linear in the Coxeter number, the equality should kick in. Okay? And this is kind of one of the really big problems in geometric group theory, and it's completely verified for n at most 6. And the conjecture, as stated up here, has been proved through the work of very, very many people. It's a giant industry by the mid-90s. But if you want this part of the conjecture, what's the dependence of the characteristic relative to the data of the group? Well, you can work out what comes out of these proofs, and the identity does hold as soon as the prime is greater than e to the e to the e to the e to the n, or something quite horrible. Okay, so there's a gap in our knowledge, and there's a huge shock when Geordie Williamson proved this fantastic theorem. I'm oversimplifying it for the purpose of this discussion. So the theorem says, assume that there are infinitely many Fibonacci numbers, Fibonacci prime numbers, Fibonacci numbers that are prime numbers. Okay? Then this conjecture is wrong in the sense that there are counterexamples, exponentially large counterexamples to this Lustig modular Lustig conjecture. Okay? This was a really shock. I mean, people believed this conjecture. They believed the bounds were right. They'd been verified. And the way that he goes, it's amazing. I don't understand a word of this paper. But nevertheless, we could, so with Peter McNamara and Geordie, we could remove this. We did not prove that there are infinitely many Fibonacci primes, but managed to circumvent it. And the way to circumvent it is exactly to go to thin orbits. So I'm not going to say very much. I'm far from an expert on modular representations. This is all I'm going to say about Lustig's conjecture. Maybe at the very end I'll give a word about how to remove this assumption. So any questions on this before we move on to something completely different? Okay. So that was Lustig's conjecture. It's not fractal. We're going to just bounce around a little bit. Let's talk about pseudo-random numbers. So pseudo-random numbers, right, these are deterministic sequences. This is what your computer is doing every time you say, give me a random number. Well, these days they have little chips that there's some quantum randomness. But anyway, for a long time, all a computer could do was some deterministic process that spits out numbers that look like they're random. And the absolute first thing that you would probably think of is the so-called linear, this is the oldest pseudo-random number generator, the linear congruential method. What do? You take a number, you multiply it by something, you add something, and you reduce mod something. Okay? And you do this over and over again, and you'll get a sequence of random numbers. Okay, how random is this map? So for simplicity, let me just take the shift to be 0, so we're looking at the homogeneous case, and I may as well start in that case with the initial seed being 1, and I just get then the graph. If I look at what sequence I get out of this, I'm just looking at the graph of n goes to b to the n mod d, the powers. Now there's some number theory that interferes, so let's take d to be a prime and b to be a generator. Then we're going to get all the numbers, all the non-zero numbers from 1 to d in some permutation. Okay? And the question is, how random is this set? So let's have a look. If there's some grad students, maybe you'll verify that 10,037 is indeed a prime number on your smartphone, and that 4217 generates the multiplicative group mod d. And here's the graph. Okay, so again, I'm graphing n versus b to the n mod d. I don't know if you can still see that. So 4217 is right there-ish, I think. So that's 1 point. And then it bounces around at random, and that little dot there is Fermat's little theorem. You have to come back to 1 at the end, right? But otherwise, it's just a really random map, and this is why it's the standard, pseudo-random number generator. You have no idea where on the x-axis you should be. Let's see how robust this is. I'll take the same prime but a different primitive root. Okay, so 4015 instead of 42 whatever. Here's the picture. Looks basically the same. We can't tell the difference. Here's 4015 there. There's Fermat's little theorem. This is robust, right? These are nice pseudo-random numbers. The sequences, you really can't tell what's going on. Both sequences look random. What do I mean by random? If I tell you the y-axis, if I say, when do I hit 6,000? Well, you know that there's some point where you hit 6,000, but where on the x-axis is the point that matches 6,000? Of course, that's the discrete log on which cryptosystems are based and so on. So that's a hard problem and a manifestation of the randomness. All right, but if we don't just use our eyes, if we do something mathematical, so let's do a calculation, we might want to do the simplest statistical test, which for sequences, okay, you're giving me all these numbers in order. What if I look at pairs of those numbers? Can I learn something about the serial correlation of pairs? Do I know something about, if I know b to the n minus 1, b to the n mod d, can I guess b to the n, b to the n plus 1? Well, obviously b to the n you can guess, you know it already, but can you guess the next power if you look at them in pairs? So let's see what that'll look like, which is the same thing, because b is a generator, this is the same thing as plotting x and b to the x, and let me divide by d and put everything in the unit torus. Okay, so here are the same pictures. Here's our first example, our same prime and 4217 as the root. And that's the picture of pairs. So that is a fantastically equidistributed grid, right? Notice how many, notice that there are, the mesh is a 1 over d by 1 over d mesh, and so there are really d squared possible places I could have put a dot, and yet I'm only putting d dots, square root of the total possible number, and yet it still looks to the eye like I filled out the entire grid. So that's a fantastic pseudo-random number generator because, again, knowing the x-axis, I really have no idea where to place the point on the y-axis. Let's just make sure this happens all the time. Let's try the other root. And that's the serial correlation of pairs. Okay, so if I know x, because I was given a whole sequence, I have a 1 in 5 chance of guessing where the next power is going to be. Okay, so this is a terrible pseudo-random number generator. Even though we couldn't see it on the level of the sequences themselves, this first naive test, the serial correlation of pairs, distinguishes the two immediately. Okay? And so the question in this theory, okay, so example 1 is a great sequence, example 2 is a horrible sequence from this statistical test. And the problem is, if I give you a modulus like this prime 10,037, how do you find a good multiplier? Obviously, you don't want to plot these things and stare at them if d is 2 to the 1,000, right? So there should be some efficient, robust method, hopefully proving that these exist. I mean, there's a whole big theory that I'm just scratching the surface of, but that was kind of the impetus for the study of linear congruential pseudo-random number generators. Any questions before we move on to something completely unrelated? Okay. Our next stop is numerical integration. So let's talk about the quasi-Monte Carlo method. So this comes from this beautiful inequality of Koksma and Klafka, which says, okay, let's say you want to integrate a function. In one variable, everything is much simpler. Let's go to the simplest non-trivial case, which is 2 variables. You have a unit square. You have some function. You're going to integrate it numerically. What does that mean? All a computer can do is sample the function at a bunch of points, and presumably you average or take a weighted average or something like this. Let's say we just average. What error do we get on this estimation? There's this inequality. What could go wrong? The function could be very highly oscillatory, and then you don't have a hope of capturing its integral by evaluating at a few points. So it could have a large variation. So let's put the variation in there. What else could go wrong? Well, I haven't said anything about the sample points. Maybe you're just sampling one corner. That's not going to give you a good approximation. So the points should be well distributed. And the right thing is the discrepancy, which I'll remind you of in a second. But the beauty of this inequality is it completely splits the error term into the two things that can go wrong, and it's just a multiplicative estimate, just the product of these two things. Okay, never mind what the variance is if you don't remember, but discrepancy is going to be important to us. So what's the discrepancy? So I have a sequence of points. These are my sample points in the unit square. I'll take my favorite rectangle R, and I look at the proportion of points lying in R, which, if the points are well distributed, should be close to the area of the rectangle. And so I take this difference, and I take the worst rectangle. Okay, so that's the discrepancy. And so if you're running just a Monte Carlo simulator, you just choose these points at random, meaning uniformly in the square, and you get some error. But the Kwazii Monte Carlo method is, I don't know anything about the function, but the points I get to choose. I tell the computer where to sample. You tell me the function, but I'm going to tell you where to sample. So the goal in this business is find sequences that minimize discrepancy as best as possible. Okay? So what can you do? All right. Well, you could take a root d by root d grid. That's kind of the most naive thing. And let me show you why that's bad. So if I have, here's my unit square, here's my root d by root d grid. Well, here's a rectangle of area approaching 1 over root d that has no lattice points. Okay? So the discrepancy will not be better than 1 over root d, which I've written as root d over d. What about in the other direction? I should have said. What's a lower bound? You know, the discrepancy going to 0 tells you that your sequence is becoming equidistributed, but it's measuring the rate at which it's becoming equidistributed. So I claim you can never do better than 1 over d. So the discrepancy of any set of d points is never better than 1 over d, simply because I can take a rectangle or a family of rectangles that zooms in on one point. So their area is arbitrarily small, and yet it's always capturing 1 over d of the points. Okay, so you don't want to do root d by root d grid. Well, maybe you do. Maybe that's the best possible. What about uniform? As I said, there's just the standard Monte Carlo method is sampling uniformly. So there's a simple exercise in the central limit theorem that says, again, you get root d, root log d over, never mind, something like root d over d. You don't do better. Purely random or purely structured does about the same and does 1 over root d. Now, I should be thrilled with that. I'm a number theorist, right? So this is square root cancellation. It's the Riemann hypothesis. Why shouldn't we be celebrating? We shouldn't be celebrating because of a beautiful theorem of Schmidt's old theorem. It says that improves on this inequality. So it says for any set of points, actually you can't do better than a constant log d over d. So this 1 over d was not sharp. Actually, you can't do better than a log off of that. And the difference from here to here is an extra square root d. That's what you would like to capture somehow. Okay, so you want to go, it's sort of like the Gauss circle problem. You get the square root for free. Can you get another square root off of that? And that's what you would really like. So that's the theoretical lower limit. You want to minimize this discrepancy. Give an algorithm that constructs sequences which get a log d in the numerator instead of a root d in the numerator. And by the way, it'd be nice for this to be an efficient algorithm, not just some convoluted thing, something a computer can evaluate.
And Alex, are you trying to get a sequence where you take the first d and it has a discrepancy, or are you sort of starting over for each new d?
So you're going to tell me I have a conference in 2 weeks, and I can evaluate this function exactly 10,037 times. Give me the points where I should evaluate this function so I get the best possible approximation I can. So you're telling me the d, you're telling me the function, I'm supposed to give you a sequence. So for any d, I want to be able to give to you an efficient algorithm that gives you this best possible place to sample. Okay? All right, so that's the Kwazii Monte Carlo method. Any questions before we move on to something completely different? This is the unreasonable effectiveness. All these things will have to do with one another. Yes, sir? Okay, wait for it. Yeah, there's a reason they're connected, right? It's foreshadowed. Yes? Is the answer known? So if you choose your points from any algorithm, actually, it doesn't matter that it's uniformly distributed. So how do you choose? First of all, the efficiency of that is questionable, because how are you going to choose points according to a random matrix? Right. Okay, how do you construct a random matrix numerically, right? All of these things become giant problems. So in a second, we'll answer both of your questions, because I'll give you an algorithm that's completely efficient, except it's conjectural. Okay, can we move on? We'll come back to all these questions. Okay, so that was numerical integration. Now let's talk about Zaremba's conjecture. So it's going to look like it's coming out of left field. I guess at the time, this is early 70s, so it's before Diffie, it's after Diffie-Hellman, but no, it's before Diffie-Hellman, it's before RSA, sort of. People didn't, I think, appreciate what number theory can do for numerical methods and numerical problems. Here's the conjecture. It's really something completely elementary. Euclid could understand this conjecture. Am I right with the time? When's Diffie-Hellman? 74?
That's 75.
Yeah, so this is like 69, 71-ish. Okay, here's the conjecture. There exists some A. Think of A as like 100 or 10 or something. There's some absolute constant. So that for any D you give me, I can find a coprime integer B so that when you write B over D as a continued fraction, these are the, A0 plus 1 over A1 and so on, which I'll write like this. All of these partial quotients, the AJs, are at most 100, or at most 10, or at most 5. That's the conjecture. Euclid could have understood this conjecture, right? This is the Euclidean algorithm. It's just finite continued fractions, rational numbers, nothing complicated here. You give this to a high school kid in Hungary or something, they should be able to solve it, you'd think. It's been around a while. So why was Zaremba interested in this? Because he proved a theorem, and the theorem is, suppose I have a fraction b over d, all of whose partial quotients are bounded by a, 100. Then, if I look at the pairs x over d, bx over d mod 1, and I take the discrepancy of that set of points, it's bounded by, I'm lying a little bit, but roughly it's bounded by 100 times log d over d. That's the same log d over d, which was best possible from the other inequality in Schmidt's theorem. Okay? So let's just look at our two fractions. Our first fraction was 4217 over 10,037. Here's the, by the way, continued fractions are extremely efficient to compute. Here it is. It's all ones and twos. So the discrepancy is like 1 over 10,000, basically. On the other hand, our other fraction was this b, which has this giant partial quotient 2,000. So 2,000 over 10,000 is like 1 in 5. Okay, that's a tiny discrepancy. That's exactly what we're seeing all the way over here in this picture. That's how you tell one from the other. You compute the continued fraction of b over d, and that's a great, those points are great points for sampling a Monte Carlo integration. This is a terrible set on which to sample a Kwazii Monte Carlo integral. Okay? So that solves, so Zaremba's conjecture, if it were true, would solve both the numerical integration and pseudo-random number problem. Of course, it's still a conjecture. So nonetheless, there's been some recent progress. As I said, this is work with Jean Bergan. We showed you can take a equals 50, and you won't get every, this isn't true for every integer d, but the set of d up to n for which the conjecture does hold, divided by n, so the proportion of d's for which it holds, has a limit, and that limit is 1. So 100% of the d's, this is the density version of Zaremba's conjecture. So almost every number. I'm asserting the existence of one b. In fact, the proof tells you how many b's there will be, and I'll come back to that in a minute. Yeah. Other questions about this?
Not only how many, but how can you actually find that?
Right. So this tells you how many. So in the interest of full disclosure, what numerical people actually do, if they're going to use this method, is they choose these guys first, like 1s and 2s, and then they do it at random until they find a d which is roughly of the size that they want, and then they integrate. Okay, so if you're happy with Fibonacci numbers, if you're only going to sample your function 8 times or 13 times or 21 times, then you take all 1s here and you do absolute best possible. But the Fibonacci numbers are quite sparse. Okay. And I should say more recently, my student Xinyi Huang, based on work of Ferlenkov and Kahn, took 50 down to 5. So some recent progress. Okay. Is 5 best possible? Okay, so from the point of view of the theorem, which is density 1, 5 is not best possible. 2 should be best possible. But from the point of view of Zaremba's original conjecture, 5 is best possible. And I'll tell you why. If you look at d equals 6, sorry, so let's take a equals 4. And let's take d equals 6. So we want coprime numerators. So the only fractions to try are 1, 6, and 5, 6. So let's compute their continued fractions. This even I can do. That was easy. And this one is 1, 5. Excellent. So sufficiently large. There's a long history of the conjectures about this. Niederreiter said if you take a equals 3, every sufficiently large number should arise. And if you take a equals 2, then a positive density of the numbers should arise. And then much later, Hensley said, actually, if you take a equals 2, every sufficiently large number should arise. And there's an even more refined conjecture, which is wrong. And I'll explain why it's wrong. It's because there's a local, potentially a local obstruction. So I'll get to all those issues soon. But just the conjecture, everybody's OK. We can move on to something else. OK. So that was Zaremba. Let's go to arithmetic chaos. So here's Kurt's conjecture. So again, this is the classical arithmetic chaos conjecture. It says the following. So you look at your modular surface, X, or its unit tangent bundle. And you want to know, does there exist a compact subset Y? So you want to cut off the modular surface at some height. The only non-compactness is the cusp. So the table is some finite height. I want to take this piece of the modular surface, Y, with the following property. You give me your favorite real quadratic field, Q adjoint root 5. I want to look at the set of closed geodesics on the modular surface, which are defined over Q adjoint root 5, and contained in Y. In other words, they move around down here. They never enter higher. The closed geodesics, these are low-lying closed geodesics. Okay? So you look at the set of closed geodesics on the modular surface defined over Q adjoint root 5 that go no higher than this height in the cusp, and you want to know that that set has positive entropy. So that's the chaos. I'll explain all these things in a second. Before I explain them, let me immediately reformulate them to something more classical where it's clear what's going on. Okay, so here's the reformulation. There exists some A, like 100 or 50 or 5, so that you give me your favorite real quadratic field, and I look at periodic continued fractions, which lie in Q adjoint root 5, with all partial quotients bounded by 100. That set should have exponential growth as the number of terms I'm allowing here goes to infinity. Okay, the exponential growth is the positive entropy. The positive entropy is the chaos. That's the conjecture. Now, why is that a reformulation? It's a reformulation because what's the equivalence? Well, the geodesic flow is a symbolic coding of the continued fraction expansion of the visual limit point. Let me explain what I mean by this. So here's a sample. Here's a point in the tangent bundle of the universal cover, just in the upper half plane. And if I follow that point to infinity, if that's the visual point, my eyes go to the boundary, I get a quadratic irrational in Q adjoint root 5. And I've chosen it so that it's exactly periodic with period 1, 2, 1, with partial quotients 1, 2, 1, 3. I connect that point to its Galois conjugate, and I fold mod SL2Z. I get a closed geodesic in the modular surface. And so this point appears here, and then it goes around. So here's the coding, 1, 2, 3. Every time we switch domains, I count. And then we switch the other way, so that was a 1. That was a 1, 2. And that's a 1. Let's count again. 1, 2, 3. We switched. And then 1. And then 1, 2. And then 1. And then we do it all over again. And guess what? We're reading 1, 2, 3. 3, 1, 2, 1. 3, 1, 2, 1 is the way we're just reading. So you just read off the continued fraction based on when you switch fundamental domains. Okay? So if you think of the geodesic as traveling here, this will be 1, 2, 3, and then I switch to the other side and so on and keep going. So that's the symbolic coding. And so if you have a closed geodesic, that means that the coding is periodic. Well, if the coding is periodic, the continued fraction is periodic. And the things that have periodic continued fractions are quadratic irrationals. Okay? So that sort of explains why I have quadratic irrationals here. Why do I have, what's this number capital A doing? How do you go high in the cusp? If here's my modular surface, if I'm going to go high in the cusp by a geodesic, I have to do it like this. And then I do something else. Okay? So this is going to go 1, 2, 3, 4, 5, all the way to before I switch to the next guy. It's going to have a whole long sequence of rights before it switches to lefts. Okay? So if I have only small partial quotients, that means I can't go high in the cusp. So that's the equivalence between the two statements. And what's the difficulty? Well, we have all kinds of techniques to control arithmetic. We have all kinds of techniques to control dynamics, and the two don't play nice with each other. Okay, so that's the arithmetic chaos conjecture. Have I answered your question about what it means to be defined over? You start and end, and that's the definition. Okay? Any questions on Mcmullen's conjecture? As I said, we have a conjecture which implies Mcmullen's conjecture, which we think is, well, it implies a bunch of other things, so maybe it's more natural. But we really can't say anything towards the conjecture as it stands. Okay, let's move on. So here's the ELMV problem. Now, it's going to sound, at first, very much like the Mcmullen problem. And there's a 10-year gap between when one was formulated and the other. And I'll try to explain why. They're really coming from completely different places. Mcmullen is studying, I didn't give the context of his problem. You know, there's this whole Margulis type conjectures, Littlewood conjectures about how do closed orbits, you know, what their trajectories look like and what their time spent in cusps and so on. So bounded closed orbits in symmetric spaces is a giant industry, and he somehow realized that, wait a second, this first most basic problem that we should be able to answer before we go on to higher rank is wide open, and not just wide open, but really we have no tools. ELMV was studying something completely different. I'll explain in a second. But here's the formulation of the question. So does there exist a compact subset of the modular surface, so far so good, with the following property? It contains infinitely many closed geodesics, so low-lying closed geodesics, which are fundamental. So now I have to tell you what I mean by a closed geodesic being fundamental. Well, we already know what closed geodesics are. There's a connection between closed geodesics and binary quadratic forms. So this is indefinite binary quadratic forms, and in fact, equivalence classes of such. And the connection is, well, okay, so binary quadratic form has this discriminant, b squared minus 4ac. You all learn in high school or elementary school if you're in Hungary or something. And you take these two roots, alpha and alpha bar, you connect them, and you close up, and every closed geodesic appears this way. So we know what it means for an equivalence class of binary quadratic forms to be fundamental. It's if the discriminant is the discriminant of a real quadratic field. So if you don't know what that means, just think of it as being a square-free number. So that's the question. The question is, can you find infinitely many closed geodesics low-lying on the modular surface with the property that the closed geodesic corresponds to an equivalence class of binary quadratic forms, which is in the ideal class of some number field, and not just some Picard group. Okay? You don't want orders. Can you find fundamental low-lying closed geodesics on the modular surface? Why were they thinking about this? Well, they were studying Duke's theorem, and in fact, they were trying to give a dynamical proof of Duke's theorem. Let me remind you what Duke's theorem says. So we'll take the class group, all the inequivalent binary quadratic forms of a given discriminant, and Gauss's famous theorem is that this is a finite set. In fact, it's a group, but never mind. For us, it's a set. HD is a class number. And let's look at these closed geodesics grouped by the class, and let's see what happens. So here's our first example. We'll take the discriminant 1337, which is square-free, so it's fundamental. The class number, it turns out, is 1. So there's one class, which is represented by the form 19x squared minus 27xy minus 8y squared. This is the quadratic irrational and its Galois conjugate. And let's look at the continued fraction of this quadratic irrational, and here it is, 1, 1, 2, 17, yada, yada, you can read. Okay, it's this weird long sequence. And here's the corresponding closed geodesic. So you can start reading off the path, the trajectory of the closed geodesic by the continued fractions, as we did before. So there's 1, 1, and then it jumps to 17, and then there's an 8 and a 5, and then over here is a 35, and that 35 shoots it up into the sky, and then it falls back down. And then it does it all over again. Okay, so this is just one geodesic. That's not so interesting. Let's look at a larger class number. So here's a number 1365, which is, again, square free, so it's a fundamental class. The class number is 4. It's represented by 4 forms. I won't tell you what they are, but I'll give you the continued fractions. So the blue continued fraction is 135. What is this supposed to be, brown or something? Brown is 5, 7. This is purple, bunch of 1s and an 11. And red is 1s and 2s. And let's see the corresponding closed geodesics. So here you have the blue. The blue is 135. So it's just going to go, shoots up to 35, and then back down. And it does it all over again. That's all this guy does. He's very boring. How about the brown? The brown goes up to 5 and then 7, 5 and 7. He's over here. The purple goes up to 11 and then back down, and then 11 back down. And here's 1s and 2s. 1s and 2s is down here, this red guy. So we want to know about these red guys. That's what the question was. Why do we care about the red guys? Well, so what does Duke's theorem say? If you saw these two pictures, except I didn't color this one, if you were colorblind, they might look quite similar. So what do I mean by that? Here's Duke's theorem. You look at the closed geodesics in the class. You put a probability measure, just giving arc length, the arc length supported probability measure on that closed geodesic. And you average over the class, so sum them and divide by how many there were. That will converge as the discriminant goes to infinity to uniform measure. Okay? That's this beautiful theorem of Duke. And the proof goes through, it's an amazing amount of gymnastics in analytic number theory. You have period integrals, Walsh-Perget formula that take you to half integral weight Fourier coefficients. You need subconvex bounds, which you get through Kuznetsov. I mean, it's really, then you have to analyze special functions. It's kind of amazing that this dynamical statement was proved in such a roundabout way, you might say. Or if you're a number theorist, you might say, look at how beautiful analytic number theory is. But they wanted to know, can you give a proof of this theorem just using something like measure rigidity? You know, there's only one possible sequence of measures that this will converge to, and maybe that's why this is true. So the question was, what are some other possible weak limits? Well, there aren't any. That's what the theorem says. You have unique, one unique ergodic measure. Well, OK, but what if you don't average? What kinds of things can happen? So let's study this a little bit. So if the class number is 1, which of course happens infinitely often, no one's going to call me on that. OK, so we all agree the class number is 1 infinitely often. I've proved it. No, we don't know that. Then there's no average, right? There's just one closed geodesic. And what happens to that one closed geodesic? Well, by Duke's theorem, it's equidistributing, which means it's going to visit the cusp. The cusp has a positive proportion of the mass. So these curves cannot be low-lying. You can't cut off the cusp at some height and look at the class number 1 guys and find low-lying curves. OK. Moreover, it's believed that, that as long as you give me any epsilon, and I move through, of course, the class number is at most root d. So if I move through discriminants, which are of size at most d to the half minus any epsilon for any fixed epsilon, individually, every single geodesic in that class should equidistribute. You should not need this averaging. That's kind of believed. And there's some partial progress towards this. What that tells us is if we want to see this non-equidistributing behavior, if we want to see other weak star limits, we have to look at giant class numbers. So the class numbers have to be as big as possible. On the other hand, we have another conjecture, which if no one's going to call me on, is that the average class number is very, very roughly n to the 1 plus epsilon. OK, so that's a wide open conjecture. If I could solve that, I'd be telling you about that and not this nonsense.
If I were to just write down a bunch of 1s and 2s and then make it periodic to get some, I would expect that to be a way of generating lots of quadratic fields with giant class number.
It should So, yes. In fact, if you take a bunch of 1s and 2s, it should give you, well, let's be a little careful. Yeah, if you give me a long strings of 1s and 2s, it's very highly unlikely that the corresponding discriminant is 1. But it's easy to construct giant class numbers. It's hard to construct small class numbers. Giant class numbers, you know, you want t squared minus 4. Anything in the form t squared minus 4 is going to have a giant class. Yeah. So producing small units is easy. Producing giant units is hard, right? Almost all the Pell solutions are exponentially large, and no one has any clue how to show that. Yeah. So yes, you would, and it's not hard to do so. Yeah. Okay. So what does this tell us? The only discriminants we're interested in are those with giant class number, but most of the class numbers are tiny. So we're looking at this is a hard problem. That's the point I'm trying to make. The number of such discriminants should be no more than square root n up to n if you believe all of these heuristics. Okay? So it should be quite a rare phenomenon to find large subsets of low-lying closed geodesics. And moreover, these guys are asking about, so if you don't put the restriction on fundamental closed geodesics, then you just give me a sequence of 1s and 2s. That's it. You just cook up the geodesic to do whatever you want. And ELMV specifically wanted to know, can you make these in the class group and not in some order? So here's the theorem. The answer is yes in this technical sense. You give me your favorite constant, 1 over a million. I'll give you a compact subset of the cusp, which means I'll cut the cusp somewhere. If you give me 1 over a million, I might have to cut it in the stratosphere, but it's some cusp, some cut of the cusp. So I have a compact subset. And I'll give you a set D of fundamental discriminants, which depend on your 1 over a million, with the following two properties. First of all, the number of discriminants that I'll find up to n is at least n to the half minus 1 over a million. So that's roughly best possible compared to what you could hope to expect. And moreover, for each discriminant D in our class of discriminants D, you look at the class group, and you look at the closed geodesics in that class group, which are low-lying, which are contained in this region Y. So how many low-lying guys did we actually find? In fact, you find d to the half minus 1 over a million low-lying guys. So it's not, it can't be a positive proportion of the class, but it's still very large. I mean, in particular, it tells you the class number itself is very large. But the class number has to be much larger than the low-lying guys. Duke's theorem is still true. Okay? So this is some strong, almost as strong as possible answer to this ELMV question. So any questions on this problem? So it's telling you that even if you restrict to fundamental geodesics, you do not have this individual equidistribution because you could have other weak limits, and these limits, whatever these closed geodesics are, they're contained in a finite amount of area. So they're not going anywhere. You can't, they were worried maybe all the other measures would just escape to infinity and there'd be escape of mass. No, you can contain them and still get weak star limits if you don't average over the entire class group. So Duke's theorem is quite a delicate thing. Questions? Okay, so why are these two problems, why did it take, as I said, almost 10 years to go from one to the other? Because they were thinking about different problems when they formulated these problems, but in fact, in some sense, they're orthogonal to one another. So just some philosophy. Both problems are about low-lying closed geodesics, but I claim arithmetic chaos is a vertical problem and ELMV is a horizontal problem. So what do I mean by that? So here's a diagram of real quadratic fields ordered by discriminant. Here's your favorite field. And above that field, you have all of the closed geodesics defined over it, or if you like, binary quadratic forms defined over that field. And there's a finite number of them which have discriminant exactly equal to D, and that's your class group. And then there's infinitely many which have discriminant D times some square. So it's still defined over the same field, but there's lots more. And what does arithmetic chaos say? For each and every field, K, I want to go up in the tower and find infinitely many, in fact, exponentially many low-lying closed geodesics defined over that field. So it's really, you're sort of fixing each characteristic every time you go, as opposed to ELMV, which you only have a finite, for any field, you have a finite number of chances to find a low-lying geodesic. And so you constantly have to keep changing your field if you want to find infinitely many. Okay? So that's the sense in which this is an orthogonal problem versus a vertical problem. It's kind of like, you know, the Sato-Tate philosophy, a vertical Sato-Tate and horizontal Sato-Tate, and these are different aspects. Okay. Any questions on any of these problems before I tell you what they have, why they're all the same? Okay. So let me tell you about this local global conjecture. So again, it's going to come a little bit out of left field, but the key player will be thin orbits. What do I mean by that? So let's motivate this discussion by an easy fact. So if I have a quadratic irrational alpha with partial quotients a0 up to al, it's fixed by the matrix gamma, which is a0110, a1110, and so on. You just easy computation. If you've never done it, do it right now. Actually, don't do it right. Do it after, so that you don't miss what I'm about to say. So anyway, this is completely standard. So you take these partial quotients and you stick them into the 1-1 entries of matrices and look at matrix products. Okay, here's another fact. If I have b over d having partial, so I put it in the unit interval, I put a 0 there. If I have partial quotients a1 through al, that happens if and only if, when I take the matrix product a1, 1, 1, 0, and so on, al, 1, 1, 0, I get the top row bd. Okay, so the denominator d, which is what I was interested in Zaremba's conjecture, ends up being the 1-1 entry in this product. And so what should you do? All of the problems are asking about bounded partial quotients. So all of the AJs should be bounded by 100. So the natural object that you should be working with is gamma A, which is the semigroup generated by all matrices of the form A110 with A ranging from 1 to 100. It's very important that we take the semigroup here, because if you allow yourself inverses, you're changing the problem. It no longer has anything to do. In fact, if you allow yourself inverses, you get all of GL2Z. So it's very important here to work with a semigroup. And in fact, for a variety of reasons, it's better to work with semi-simple Zariski closure. So I'll take even words in these generators, because they all have determinant -1. No big deal. Okay. So that, I claim, is a quintessential thin. Well, it's not a group, so I have to call it thin semigroup, or it's thin. Which means I have to tell you what thin means. Now, if I had a group, I would just tell you its infinite index in SL2Z or something. But what does it mean for a semigroup to be thin? Or more generally, what does it mean? I have a general definition of thinness. So I'll give you the definition by giving you an example. So the Zariski closure is SL2. That's an easy thing to check. And what happens to the integer points in an Archimedean ball in the Zariski closure? So if I look at SL2Z, I take my favorite norm, and I take a large Archimedean ball. At classical exercise, there are about n squared points. What happens in gamma is an old theorem of Hensley's that the number of points in gamma in a ball is asymptotically n to the twice delta A. What is delta A? It's the Hausdorff dimension of the Cantor set, which is the limit set of this group. So what does it look like? I'll give you the example when A equals 2. So the Cantor set, by definition, is just a set of all partial quotients. Let's put it in the unit interval, all arbitrary sequences with partial quotients bounded by A. So when A is 2, let's look at this digit A1. In the interval 1/2 to 1, this digit is 1. And in the interval 1/2 to 1/3, this digit is 2. And anything here, this first partial quotient, the first digit, is already bigger than what we're allowed to take. So all of these numbers are cut out. So it's hard to draw a Cantor set, so instead I'll draw a circle for every region. The diameters of these circles are what's being cut out. So you should think of, if you start in the upper half plane, you start falling, you sort of bounce around. If you ever make your way down to the real line, then you're in the Cantor set. Okay? So that's this Cantor set, and it has some Hausdorff dimension delta. And that dimension for any finite A is strictly less than 1. And what that means is, let's compare the counts. It's n to the twice delta versus n squared. So gamma has 0 density in an Archimedean sense in the integer points of its algebraic geometric closure. Okay, so that's my definition of thin. A set S in ZD is thin if you take its algebra, you take its Zariski closure, you take the integer points of that, and if in an Archimedean ball, in that, if S in an Archimedean ball has 0 density in the integer points of its algebrogeometric closure, then I call it thin. How do you count any of these things? I don't know. But how do I tell a group is infinite volume? I don't know that either. You give me a bunch of matrices in GL and Z. I don't know that it's geometrically finite. There are all kinds of questions. But that's a definition. And most importantly, it's a definition that applies to semigroups as well as groups. And when the semigroup is in fact a group, the two definitions agree. That's an easy lemma. Okay, so it's just a variation. Okay, we have this 0 density thin subgroup, sub-semigroup. And some facts you need to know about these dimensions. This dimension, delta 2, has been studied for like 100 years. It's something 0.53. And as you relax A, as you let the size of the partial quotients get larger and larger, well, I don't think it has to do with square-free numbers that much, but zeta of 2 does make an appearance. We know the rate at which these dimensions are going to 1. Okay, so that was thin orbits. So what's the local global conjecture? Well, so let me put it this way. You give me your favorite affine linear map, which is integral on SL2Z, say. For example, what kind of maps do I care about? How about, if for the Zaremba problem, I want the 1-1 entry. So let me take the 1-1 entry. That's an affine, in fact, it's a linear map. Okay. So what's the question? Well, what is the Zaremba problem? Which numbers arise as the 1-1 entries in these semigroups? So what's the image under F of this semigroup gamma A? That's exactly the problem. Well, what can go wrong? You might have local obstructions. So for some integer q, there might be an integer n. So you're looking at an integer n. Does it arise in this image? Well, if it doesn't arise in the image mod q for some q, there's not a chance in hell it's going to arise in the image, right? That's a local obstruction. And we call n admissible if it passes all local obstructions. Now that looks like you have to check infinitely many things, because you have infinitely many q's to check whether it's there or not. No, that's very easy to check. Thanks to strong approximation, we have a semi-simple Zariski closure. And so for q outside of some small bad number of q, which are effectively computable, you know what gamma mod q looks like, and you know what f is. So everything is nice. So admissibility is easy. Now, if a number is admissible, what do you think its multiplicity should be? So let's do a silly little calculation off to the side. So here's gamma intersect a ball of size n. Okay? Here are my points. The function f is an affine linear map. So here's f, and it's linear, so if these numbers are of size n, the image is going to be of size n. Let's say from minus n to n or something. So if I take a typical number here, little n, I want to know what's its fiber. How many guys upstairs map down to little n? Well, I know the size of this. So the number of these points is roughly right there, n to the 2 delta. So the multiplicity, I mean, if I take gammas, I take the entire ball, and I see what's the size of the fiber. How many of them project onto my given little n of size capital N? What do we expect? Well, the total number is n to the 2 delta. And there's n numbers that it could possibly fall onto. So if there's no conspiracy, the fibers should be roughly distributed. So there's the n to the 2 delta from the total multiplicity. And then I should divide by n because the map is linear. And let me give myself an epsilon just to be safe. That's the conjecture. It's the most naive thing. I think it's, if I put not a gun to your head, but if I said, just give me your roughest conjecture about what should happen, this is what you might say should happen. And that's what we say should happen. And the surprising thing is that this conjecture captures all 6 of the other problems that we were just discussing. Okay. Notice, I should tell you why does it capture them. So twice delta minus 1 is the exponent here. And for as soon as delta 2 is already bigger than a half. So this exponent is always positive. So for sufficiently large numbers, somebody, I think Kieran asked why a. So if you take a equals 2, already you have a positive exponent here. And so if you believe this conjecture, then if n is sufficiently large for the dynamics to kick in, the multiplicity should be non-zero. In particular, it should the numbers represented. Okay. All right, so that's the local global conjecture. If I can take 1 minute, let me just say a word about what goes into this theorem. There's an easy fact that if trace squared minus 4 of a given matrix is square free, then the corresponding closed geodesic is indeed fundamental. And of course, it's taken out of gamma A, so it's automatically low-lying. And what's the theorem? Well, it's a sieving theorem. The trace, if you look at how many guys in the ball have trace squared minus 3 square free, trace squared minus 4 being square free, you get almost a positive proportion. And if you had the full conjecture, you would get a positive proportion. You should lose 1 over zeta of 2 by restricting to square frees. We lose n to the epsilon instead. Okay. What are the ingredients? So it's a sieving theorem, so there's going to be analytic number theory. You sieve, you break things up into main term and error term. On the main term, we're using additive combinatorics, sum product, and expanders. There's a picture of an expander. And because we have semigroups, I can't, I'm raised on automorphic forms and representations, and what is upper half plane modulo a semigroup? You lose all of this geometric structure. So it's replaced by thermodynamics, Rel transfer operators. We go to the symbolic coding, and the congruence version in Bergan, Gambert, Sarnak. For the error term, it is not enough. So this is what I mean by the beyond expansion program. We have some error term, some polynomial. I'm lying a little bit, but pretend we had a polynomial error term. In other words, a power savings error term in the count, uniform in Q. We almost have that. Even that is not enough. So what we need to do is develop new bilinear forms techniques and prove an average version of what would be the analog of a Selberg 1/4 or a Ramanujan type spectral gap. The exponent we obtain is 15/32, which pales in comparison to what we would know if we had SL2Z instead of this semigroup, which is 7/64. So this is 30/64. The thing about 30 is it's less than 32. So it is a spectral gap. So half is the trivial, 1/2 is no gap at all, and we get some gap, and that gap is numeric. The fact that the gap is numeric means we win. If you take an arbitrary gap, it doesn't work. Okay, I'm out of time. So again, that picture was the motivation. Here's some, so this is the latest paper. It's on arXiv, and then this is here's some survey that'll explain some of these things because I went too fast. Okay, I'll stop there.